everyone. So believe it or not, this is our final lesson for our magnetism unit, which is crazy, but well, here we are. And so this final lesson is on a concept and process known as electromagnetic induction, which sounds very fancy because it is. So let's go ahead and dive right in. So just to review where we've been so far during this unit. So we started off in our first lesson really focusing on this idea that magnetic fields and magnets are created by electrical charges that are moving. And so that can be in the form of an electron orbiting around the nucleus of an atom. It can take the form of a current, but either way, at the heart of all magnetic fields and all magnets, there must be some moving electrical charge, right? And so once we've got then this moving electric charge and this magnetic field, what we find is that they'll exert forces upon each other. A magnet will exert a force upon a moving electric particle because ultimately that moving electrically charged particle has its own magnetic field, which is then going to interact with this second external magnetic field. So we start to see these magnetic forces taking place between different sources of these magnetic fields. And we can predict what these interactions look like, the fields that are being produced, as well as the magnetic forces being exerted upon charged particles, using our right hands, our best friends, during this unit. Now, just to give you a chance to kind of see some of these ideas in action, I would like to show you a motor. And motors take lots and lots of different forms here, but we're going to go ahead and focus on a nice, simple little motor that you could actually make at home if you had the materials and the desire to do so. Let's go ahead and see what happens here. All right. Ooh, we're going to pause that for a moment. We're going to get rid of this ad because I hate it. So let me show you the basic setup of what it is that we see here. So we've got in the center here just an ordinary AA battery. And at the bottom of the AA battery, we've got some very strong neodymium magnets. And then what the person is about to do is place this loop of wire over the battery so that this little point right here in the top center is touching the positive terminal of the battery, just resting upon it. And then the loop swings around and then just gently touches down here at the bottom where the magnets are. So now we know what's going on. Let's watch. Woohoo! It spins. Look at it go. And then, plot twist, if we flip the magnet over so that the other pole is touching the battery, the motor, it's not an engine, it's a motor, will still spin, but in the opposite direction. Gosh, that's cute. All right, so based on what you've just seen here, what type of energy is providing the input for this motor? Well, what I see is that we're starting with a battery, which means that we must be starting off with, well, in the very beginning, chemical energy, but then what's really being used here is electrical energy. So we're starting off then with some sort of source of electrical current, some sort of electrical energy. And then what type of energy then is the output of this motor? Well, the big exciting ending of this device's functioning is that the wire spins, and if it's spinning, it's moving, and if it's moving, and we can see it, that's got to be kinetic energy. So then a motor converts electrical energy into kinetic energy. So it starts with an electrical current moving charges, and that produces some sort of movement at a larger scale that we can see using magnetic force. Now, to see what exactly that looks like, we can see this diagram right here, very similar to what we saw in the video. So we know then that with the wire connecting the two terminals of the battery, there's going to be a current that flows from high potential down to the low potential side. Right? But as that current is moving through from high potential to low potential, it's also moving through a magnetic field that's being produced by the magnets at the bottom of the battery. Now, we know that magnetic field lines always form closed loops, and they get just bigger and bigger out in space, but they always loop around from the North Pole to the South Pole. So what we can see here then is that overall our current is moving down the battery. Our magnetic field lines are moving out away from the battery. And so we see that they're at least partially perpendicular to each other. And so then we can just use our right-hand rule. We take our thumb in the direction of the current, we take our fingers in the direction of the field, and then we're able to figure out, based on which way our palm is pointing, the direction of the force exerted upon the wire. We see on the right-hand side of that the force is coming out towards us, and on the left side of the wire that the force is going into the page away from us, and so that produces this nice happy spinning motion. Yay, motor. All right. So that's all good. Okay. So so far we've already talked very extensively about how moving electric charges will create magnetic fields. But here's our final big idea for this unit. It turns out that magnets can also create electricity. So electricity can create magnets. Magnets can create electricity. Now, if you haven't already done the 7.4 investigation on Google Classroom, pause, stop, go do it now, because it's fun. You get to play with a simulation and make electricity, and it is wonderful. If you have already done that, though, please continue and proceed at this point. Right? So the big takeaways from that investigation where you were trying to create electricity was that if we want to induce an electrical current, if we want to get a current to be created and charges to move using magnets, what we really need is to be changing the magnetic field that's going through our loop of wire. And there are a number of different ways that we can do that. We can move a magnet physically in and out of the loop of wire. Some of you may have tried flipping the magnet, so switching the polarity of the magnet. That also was able to create an electric current. Or this wasn't really an option in the simulation, but it stands to reason that instead of moving the magnet, we could just move the wire around the magnet, and that would have the same overall effect. But the key idea is that the field has to keep changing. We have to keep moving the magnet, moving the wire, switching things around. As soon as things stop moving, the current stops flowing. All right? And the faster and more dramatically and more drastically that magnetic field changes, the bigger the current is going to be. So that could mean moving your magnet faster. It could mean using a stronger magnet so that any movement creates a bigger change. It could mean using a solenoid with more coils in it, because then there's more coils there to sort of be picking up on that change in the magnetic field, and that produces a bigger current as well. So lots of different ways that we can try amplifying that current. All right, let's do some demos, all right? Because that's all cute and like simulations are fun, but you know, it's also fun to actually just see the darn thing. So here's what I've got in front of us right here. So we've got our galvanometer again, which as a reminder measures current. So we'll be watching this little needle here to see what's happening with the current. And then connected to the galvanometer, I have this coil of wire. And we've gone ahead and removed the insulation from the two ends of the wire so that we're able to create a complete circuit over here. And then I've got a nice bar magnet, North Pole, South Pole. And so just as we saw in the simulation, I can see that as I'm moving the magnet so that its field through the loop is changing, we see an induced current, and the current goes one way as I push the North Pole in, and the opposite way as I remove the North Pole. Now, if I were to switch this so that now I'm going to put the South Pole in, what do you think is going to be different about this? Well, ultimately, we see that the direction shifts. So now as I put the magnet into the loop, the current is in the positive direction, and as I remove the magnet from the loop, then the direction of the current is negative. Okay, and I can see that the faster it moves, the bigger the current, the slower it moves, the smaller the current. But as soon as I stop moving the magnet, the current stops as well. It has to keep moving in order for that current to continue to be induced. All right. That's cute. Okay, let's do something else, because the galvanometer is like fine and all, but sometimes we want a more relatable way to see that a current is being produced. And last unit, we used light bulbs for that a lot. So what I have here is a light bulb that is connected to this device right here, which has on the inside of it something very similar to what you saw just now, as well as in the simulation that you played with in the investigation. But in this particular situation, what's moving is the loop of wire. So there's magnets inside of this, which I know you can't see because it's in a casing here, but there's magnets inside of here, and then this loop of wire that's connected to this cable here that that spins as I move this crank. Okay, now if I move it slowly so that the loop of wire is moving slowly, nothing too much. But if I go faster, oh my gosh, there's light, yay! But if I stop, no more current. All right, so just another chance to kind of see this process in action. Now it turns out we have a special name for this type of device, and that name is a generator. All right, so a generator is any device that converts kinetic energy into electrical energy using this process of electromagnetic induction that we've been talking about here. Okay, so again, either we're spinning a loop of wire in a magnetic field so that the magnetic field through the loop is changing depending on the loop's orientation, or we're moving the magnet in and out of the loop of wire, but regardless, we get that changing magnetic field that induces a current in the wire. If any of you have ever seen those shake flashlights where you like shake it back and forth and that's what powers it, all you're doing is shaking a magnet back and forth through a loop of wire. That's it. It's just a generator. That's it. All right. Now this idea of a generator converting kinetic energy into electrical energy, that should sound semi-familiar to you. Because at the start of this lesson, we talked about these devices called motors. We saw one in action in a video, and now I'm talking about generators. So here we have diagrams showing the inner workings, or possible inner workings, of a motor and a generator. I want you to take a moment, look at each of these diagrams, and try to identify, these look really similar, what's different about them? Now in both cases here, we have a magnetic field going through the center, pointing from the North Pole over to the South Pole. We have a loop of wire that is capable of rotating and spinning within this magnetic field. But the big difference is our motor has the loop of wire connected to a battery. The battery then is able to provide energy, electrical energy, in the form of a current running through that loop of wire. And as the current runs through the magnetic field, it feels a force that causes the loop of wire to spin. So we see electrical energy turning into kinetic energy. Now the generator, on the other hand, it doesn't have a battery to provide the energy. It has a light bulb which requires electrical energy. And the way that that's produced is through the process of physically introducing and providing kinetic energy to this generator. So you take the time to spin the loop of wire within that magnetic field. It induces a current, so it converts that kinetic energy of moving the loop of wire into electrical energy, which allows our light bulb to light up. So what this really means is that motors and generators, they're essentially kind of the same thing. It's the same general setup, just with different input and output energy. And just to kind of highlight that for you a little bit more, I've got one final demo. So here we go. Let me get this set up for you. All right. So we're going to jump back over here. Now I've got my hand crank generator still. And now what I've done is, instead of connecting it to a light bulb, I've connected it to another hand crank generator. All right. So I've taken this and connected the two alligator clips for it to the two alligator clips for another identical device. Now when I turned this crank before, when it was connected to a light bulb, the light bulb lit up. But now that it's connected to this other hand crank generator, oh, well, that's cute. All right, so I see if I take this one and I rotate it, the crank on the other side moves. And if I do this one, then that crank moves, which basically means that these devices can function as either generators or motors depending on what type of input energy they have. So when I turn this one, for example, this is being used as a generator. I'm putting kinetic energy in, and then electrical energy is coming out. But then that electrical energy, that current, travels over to this one, which then causes that loop of wire in there to get this magnetic force, which causes it to spin, which turns this crank as well. So motors and generators, same thing, just different inputs, different outputs, different beginning, different ending, but otherwise, same thing, which is kind of cute. All right. Which means that basically this whole unit can kind of be summed up in two key ideas. Moving electrical charges create magnetic fields, and moving magnets create moving electrical charges. All right. So it's this big, like, happy, never-ending cycle here where if we've got electricity, that electricity is moving, those charged particles are moving, and in the process of doing that, they create a magnetic field. But if we get our magnetic field to move and change, that's also then going to create electricity. So it just goes around and around and around, and it's lovely. All right. So let's take a moment just to check your understanding on all of this. So say we've got a bar magnet moving toward a solenoid, as we see right here. And the solenoid's not connected to a battery or anything like that. It's just kind of like hanging out. It loops back over. Maybe it's connected to a light bulb, whatever. All right. So how will the current that's being induced in this solenoid be affected if we use a weaker magnet? Well, weaker magnet means that as we're moving our magnet towards it, there's not as big of a change in the magnetic field. So weaker magnet's going to mean less induced current. What if we were to move the magnet faster? Well, faster movement for the magnet means a more rapid, dramatic change in the magnetic field through the solenoid. So faster moving magnet means a bigger current that's being induced. Last thing to consider, what if we were to keep everything the same, but we flipped the magnet so that the south pole is approaching the solenoid instead of the north pole? Well, if we flip the magnet, we're going to flip the direction of current as well. So that's a few different things that we can do to kind of play with this current that's being induced. Last thing I want us to consider before I am done, all right? So we've been working on this project in which we have been analyzing this mystery device right here. And based on the data that we've collected and the materials that we found, we've been assuming that this is a speaker. And that is a wonderful assumption, and we're going to keep going with that assumption. But just for fun, I want to ask for a moment, could it be a microphone? Could this be a microphone and not a speaker at all, as it turns out? Take a moment and consider, if you think yes, how? How could it be a microphone? And if not, why could it not be a microphone? Well, I would argue that assuming we were able to get an appropriate jack to plug in to some sort of device, that this, in fact, totally could be a microphone, just as our generator is also able to serve as a motor as well. So if we look at this diagram of how a microphone works, what we see is that as sound hits this device, hits our microphone, there's a diaphragm that's able to vibrate, pick up on those vibrations from the sound wave. And that ultimately moves then a permanent magnet in and out of a coil of wire, and as it does that, it induces a current, and by reading that current and the fluctuations of that alternating current, we're able to read that signal. And that looks an awful lot like the setup of our device right here, that if we were to talk into the cup here, that's going to vibrate the bottom of the cup, which is going to vibrate the nail, which is going to cause the magnet to move up and down, in and out of the coil of wire, which is going to induce a current in the wire in time with our talking, the sound that we're producing with that. So we're going to keep assuming that this is a speaker, but just to blow your mind a little bit, yeah, this could totally be a microphone too. Whoa. Okay, you know what? I'm done. You're great. Have a lovely day.